What if I told you that there are lasers in space and that we can use these lasers to explore the formation of massive stars, one of the fundamental mysteries that astrophysicists are trying to solve today? Hi everyone, my name is Philippa and I'm an astrophysicist at the International Centre for Radio Astronomy Research. Now, when I first said space lasers, you probably thought of something like this: a lightsaber from Star Wars, which is being very cutely modelled here by Baby Yoda. However, the space lasers that I'm going to discuss today are naturally occurring, so unfortunately I won't be proving the existence of intelligent alien life in this presentation. But first, please forgive me because I have slightly misled you. I actually study masers, which are the microwave equivalent of the optical lasers that you're probably used to. They operate in the exact same way, just at a lower frequency. In this diagram, we have a red atom or molecule in an excited energy level. A photon comes in and interacts with the molecule, causing it to fall down to a relaxed energy level. Now, since energy must be conserved, the energy that the molecule loses as it falls down gets converted into another photon. So now we have two photons leaving the system, which are then free to interact with more molecules. This leads to a beam of microwave photons leaving the region, which our telescopes are able to detect as masers. Now, there are a wide variety of molecules that undergo this process in space, but today I'll be focusing on my two favourites, water and methanol masers. Okay, so that's the space maser side of things done now. Let's explore massive star formation. First things first, how massive are we talking? High mass stars are defined to be 10 times the mass of our Sun, with some stars being a few hundred times the mass of our Sun. These stars are extremely rare, accounting for about 1 in 100 of the stars in our galaxy. So why do we care about these massive stars? Why can't we just focus on average mass stars like our Sun and ignore the tiny fraction of massive stars? Well, these stars actually produce the elements that are the building blocks of life here on Earth, such as carbon, nitrogen, oxygen, and iron. As Carl Sagan famously said, we are all made of star stuff. As I alluded to in the beginning, astrophysicists don't exactly know how these stars acquire their mass. So my research on space masers can help answer one of these key mysteries of the universe. However, what astrophysicists do know at the moment is that there are 4 key stages of massive star formation. We begin in the quiescent phase, where cold hydrogen gas gravitationally collapses into clumps to form a dense prestellar core, which can be seen in the black region in that image. The second phase is the protostellar phase. So here the core pulls in and accretes more and more gas and dust and heats up its surroundings, as seen in the red clumps in that next image. The next H2 phase, the gas and dust surrounding the forming star is further heated, causing hydrogen to become ionized. So here the electron is stripped from the hydrogen nucleus. We can see this in the large yellow area in that image there. Next up, we have the photodissociation region, or PDR region, where the hot baby star produces ultraviolet radiation, which we can see in the shockwave ridge between the red and the green ionized and whole molecular gas. Now, because masers emit at a lower frequency than traditional lasers, we can't use an optical telescope to observe them. We instead must use radio telescopes like this one here, located in northwest New South Wales. For my study, I needed to know the positions and locations of the massive star-forming regions and the water and methanol masers. For the positions of the star-forming regions, I used data from the MALT 90 survey. For the water masers, I used data from the HOPS survey, and for the methanol masers, I used data from the MMB survey. All of these surveys used Australian radio telescopes like the one pictured here. I then cross-matched these catalogues to find out if there are any water or methanol masers associated with the massive star-forming regions, and if I could see a trend between the number of masers and the phase of the star formation. And this is what I found, so I'll give you just a moment to digest and explore this plot yourself. So as you can see on the horizontal axis, we have the stage of star formation that I outlined a couple of slides ago. increasing in age and temperature from left to right. On the vertical axis, we have the percentage of star-forming regions that contain masers. The orange and square points show the methanol maser data, and the blue and circular points show the water maser data. The key result here is that there is a higher proportion of both masers found in the protostellar phase of star formation. So let's explore why that might be. So here is an artist's impression of what a protostar might look like based on various models and observations of star formation. The first thing we can see is this jet of high-speed particles coming out at the top of the protostar. These particles collide with water molecules, which causes their excitation and hence their maser emission. We can then see an accretion disk around the protostar, which heats the gas and the dust. This gas and dust then emit infrared radiation, which excites the methanol masers, causing them to maze. From the plot, we can see that the masers remain active in the H2 region due to the continual heating of the gas and dust and the presence of the outflow. However, we can see that the masers turn off in the PDR regions as the ultraviolet radiation and extreme heat from the baby star breaks apart the molecules, so we have nothing left to maze. So, in summary, I've shown you that water and methanol masers are found in regions of rare high-mass star formation. Both of these masers can be used as signposts for active stages of star formation, the protostellar and the H2 stages. These masers are extremely valuable as they can focus future observations and enable astrophysicists to collect more information to understand the mystery of massive star formation. So I will leave you with my email address. If you have any questions, please contact me, or if you want to collaborate in this exciting area of astrophysics, I'm always open to more friends. So thank you.